So we're going to talk today about from nanoscale to macroscale, creating new hierarchical materials for the benefit of society. And what we start with is nanoscale building blocks, what I like to call the Nano Toolbox, which has nanoscale objects from nature, folded proteins that we make, nanoparticles, nanotubes, nanolayers, and assemblies, simple assemblies of these where we can distribute the nanoparticles and tubes and stuff among polymers, or make connections between nature's own polymers and nanoparticles to do neat things. What's special about nanoscale building blocks is really just two things. They have size confinement. So properties, all of their properties change as you decrease their size below about 100 nanometers. And also, because of their very small size, they have very large surface to volume ratio, surface areas relative to volume. And so there are many interface effects which can particularly influence the environment around them. So if you put nanoparticles into, say, a polymer or plastic, you can affect the properties in dramatic ways. Now, Mother Nature, long before we ever got started with nanoscience and nanotechnology, learned that what you do at the nanoscale, at the atomic and nanoscale 1 to 100 nanometers, needs to be transitioned into the microscale and up into the macroscale where we live to affect us and society. And so as technologists, we're learning to do the same thing, starting at the atomic, nano, micro, and macro scale to utilize what goes on at the nanoscale. But what we're doing is almost like playing the game of Legos, where the nanoscale building blocks are, of course, much smaller, but you make them into assemblies. But then through the architecture that you learn, can create all sorts of assemblies that will affect our life in the macroscopic world. Let me show you some examples from work at RPI in the last few years in the center. One can create nanoscale surface features by evaporation and by single layers or multiple layers, very often at the microscale. One can change the refractive index, the optical behavior of these materials in very well-controlled ways over wide ranges. Now that you can do this on polymer sheets, plastic sheets, one can mold these in various ways and use them, again, at the macroscale to, for example, to coat solar panels very effectively to save energy. Similarly, one can take nanoparticles and disperse them in a polymer, or as one needs to do in terms of making the encapsulation for LEDs, light-emitting diodes, for use in our life all around us. One can even attach nanoparticles to the primary nanoparticles to create color control in these LEDs. But of course, what's happening at the nanoscale needs to be transitioned to the microscale in these LEDs, but then used at the macroscale in our offices or houses or hospitals to control the light for a variety of reasons. Similarly, one can take polymers, which form a lot of useful materials, in this case for the making of paper on these huge machines. This is the size of a football field, although it looks sort of small here. And the nanoparticles can prevent the polymers from forming their natural stereolytic supramolecular morphology as shown here and break it up. And what's valuable there is the properties change dramatically. What is normally a very easily worn fiber made from these polymers can be made wear-free. In other words, before and after wearing, there's no loss of material. And this, of course, is very, very valuable in industry when one has to change belts that are football field size. There's a huge cost in money. And final example, in the nano bio area, cells, which are micro size, interact with materials through proteins, which are at the nano size. And through this protein interaction between, in the middle between the cells and the surfaces, we have shown that, in fact, at the nanoscale, you get enhanced behavior of the cells on nanoscale objects as opposed to microscale. And this is a very important thing in terms of implants, be it a knee implant shown here or any other types of implant in the body. I have one actually in my leg today. That's why I'm limping a little bit from a trekking accident over the Christmas holidays. But again, the nanoscale transitions to the macroscale to influence our lives in a positive way. And of course, one can imagine today many, many different applications in terms of lightweight materials for deep space investigation, LEDs, implants, robotics, all the sort of things that one deliverables in terms of medical devices, and again, the clean hospital rooms and clean operating rooms. But all of these may seem like they're all for the future, but in fact, in this century, in the decade before, if you just went out into the street, this one happens to be a street in Stuttgart, Germany, and look at a pretty conventional street scene, if you look at this, not with conventional eyes, but with technically trained eyes, you see that there are actually many applications of nanotechnology, nanomaterials, present in our daily lives, from sunscreens to artificial lenses and eyes, to magnetic recording devices, to implants, many, many applications already present in our lives that we really don't normally know about it, but if you looked with a very trained, technically trained set of eyes, you can see them. And so what's important to remember about the nanoscale is to remember what happens at the nanoscale does not remain at the nanoscale. It transitions to the macroscale in order to benefit society. Thank you.